Welcome to today's webinar with the title Advanced HDI Customer Success Story. PCB design for a smartwatch with special guest Lukas Henkel. I am Andreas Schirb, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speakers in today's webinar are Lukas Henkel from OV Tech GmbH, Helene Ströbel and Michael Kress from Würth Elektronik CBT. Welcome Helene, Lukas and Michael. And now I wish you lots of fun and new information.
So, welcome. I'm Michael Kress. Since 30 years I work from electronics and for our customers in their development, and always I particular to their project with very interesting processes, and here I get information what the customer needs in his new project, and this is for me very important that I can make this for our inner in the plans to make new processes with new materials. Now we show you in our webinar today a lot of information about this one, and I hope you have very fun. Helene?
Thank you so much, Michael. So also from me, a very warm welcome. This is very impressive that you're listening and watching us from nearly around the world. And for my person, well, I am also very happy to be a colleague of Michael Kress at the Technical Project Management Department of Würth Elektronik. I have absolved a MBA in Strategic Management in California. So hello, guys. That was a great time as well. And yeah, since then I have consulted several national, international technical projects. And after now it has been 6 years, I am a member of Würth Group, and especially in Würth Elektronik, I'm very happy to be at the heart of the innovation technology for the PCB. So we are ready to get all your questions, to give you some answers, to consult you and to find solutions to any problems you encounter in your designs. Yeah. Just to jump into the wonderful webinar of our advanced HDI technology, I would just quickly lead you through the agenda. We will start with the basics of the technology. Then I will lead you through the manufacturing process. Then, of course, the most interesting part follows, and we give the stage to our special guest, Lukas Henkel, with his great innovation. And after Lukas reporting to you and us, my colleague Michael Kress will again jump deeper into design rules. He will refer to a certain interesting project, and we will give you a little bit information of what our physical PCB samples are constructed in, and we will show you an easy possibility to order those. So we jump into the overview. Yeah, it's easy to see. We have a any-layer microvia technology, the advanced HDI. This is a very thin stack up consisting of individually laminated layers, and the possibility to do that give us a very thin basis material. This basis material has excellent material properties, such a high TG value of 260 degrees Celsius and a reduced CTE value of 6 ppm. In comparison to that, if you take a standard FR4 material, the CTE value would be at 16 ppm. So this gives us excellent dimension stability and outstanding registration accuracy between all the layers. So as the aspect ratio rules teaches us, given a thin material, we are able to provide a very small diameter of laser drilled microvias. And this is laying at 70 microns and resulting in small annular rings, giving us the possibility to reduce the pad size to 200 microns. So overall, consider the fine layout, we are able to provide you with a fine layout of 75 microns in line space design, or even to go further to 50 microns. Very important point to mention at the end, last but not least, important overview, is that we try not to use the PTH. We are not using true hole microvias. We are working just solely with laser drilled microvias here. I will take on with the manufacturing process. The manufacturing process here in the advanced HDI begins with the core. We have a 50 microns core, and we are starting with the laser drilled microvias and copper filling process. And afterwards, we are etching the copper thickness down to an optimal of 25 microns. So as soon as the core is electrically connected, we are proceeding with the further lamination steps. If we have, like you can see here, a 4-layer advanced HDI, we are taking the next step from the top layer to the layer 2, and through same process of laser drilling, microvias and copper filling, we give the electrical connection from the top to the core, and doing the same from the bottom to the layer 3. So if we have interconnected all the layers in this manner, here you can see the staggered microvia possibility. You can have also a stacked one. Afterwards, the normal PCB production process goes on. We have, after laser drilling and copper filling, the photo patterning. We have the solder mask. After all, we have the electrical tests, surface finishing, cutting, and the final processes at the end. So this manufacturing process could leave us to a stack-up layer from 4 to 12 layers. Here on the next slide, we are presenting you just an example of a 10-layer advanced HDI. What do we need that for? What do you need that for? It would be very nice to work with as thinnest as possible materials. So preliminary, we would take a 50 microns core. We would work with a very thin isolation foil of 40 microns, which enable us to have a very small diameter of microvias. And then you can see in the table on the lower part, right-hand side, we will end with a very thin stack up. 4 layers, for example, you have a 0.25 millimeters, and going so far to the 10 layers stack up, ending round about 0.6 millimeters. So this is a very thin, high density PCB. And to jump to our application slide, It is, of course, our duty as a PCB manufacturer to follow the market tendency. The market tendency is obvious. It is all moving towards miniaturization. We have a smaller BGE pitches. We have a requirement of space saving, of signal integrity, and very efficient thermal management. And all this is possible giving these materials and this process. And in any branch which is displayed by the picture here, we are open to work either with EMS or with original manufacturing, original equipment manufacturer. You're very welcome to contact us at any stage of your innovation. And speaking about innovation, I would now hand over to our special guest, Lukas Henkel from OV GmbH based in Erlangen. And yeah, we are very excited to see your presentation. Lukas, the stage is yours.
Thank you very much, Elena, for the introduction. And thank you everybody for tuning in. It's great to be here and being able to show you what we are doing with our open source smartwatch project. First of all, I would like to walk you through a short presentation just to give you a broad overview of what we are doing, what the idea behind the open source smartwatch is. Why is it open source? What's the business model behind that? Then give you a brief overview of how the watch is constructed, what different technologies are we using, of course, with a special focus on PCBs in this case. And afterwards, we'll jump into Altium Designer and also into our 3D modeling tool to give you better insights into the current status and into the design of the watch as it is right now. So to start, we are building an open source smartwatch that is modular and community centric. What does it mean? It means we are trying to build an ecosystem where everybody can build on our platform, be that for commercial purposes or just as the end user or the prosumer that would like to get some insights into the design. Both is possible. We really would like to try and make the design as accessible as possible. That means we will open up the hardware design resources from mechanical design to the PCB design, but then also going forward, the firmware design will be published as well. And by that, we hope to invite a lot of collaboration, a lot of customizations of our platform, be that, as I said, from for commercial purposes or for personal interest, if you will. The reason why we decided to do this open source is, of course, if you'd like to invite companies to build on our platform, there's a huge incentive to build trust with those companies. If you are building a wearable device on your own, you of course would like to have complete ownership of the design, meaning if you are designing on something pre-existing, you would like to have access to all the design files and of course also have the right to use all those design files. And in order to build that trust, we decided to make it open source. And also what we like to do is initiate a know-how transfer. So on wearable design or consumer electronics, a lot of knowledge, unfortunately, is kept behind closed doors. So unless you're working at those companies, there's really no way to be a profit or to build upon the knowledge that was created within those companies. And we would like to change that by opening up our designs and therefore also transferring our know-how to everybody who would like to build on our platform. To give you a short overview of why this design is modular, I think it can be seen quite well here in this explosion view. The smartwatch currently consists of three main modules. The top module is the display module. It's a touch AMOLED display with a rounded cover glass on top. This is also, of course, something that can be customized later on. This is another unique aspect of the open source smartwatch concept that we are presenting here, that every module on its own can of course be modified. So for example, e-ink display is an option for later on. We have different sensor variations for the sensor module, but I'll dive into that a little bit deeper later on. In the middle, we have the compute module that consists of the aluminum frame that also houses the mounting hardware for the wrist-worn straps. We have the digital crown, a USB-C interface, as well as a user button, and of course the main board with the SiP itself. The sensor module is the last module that's also in contact with the skin, whoever was the smartwatch. There we have, as the name implies, all the sensors for heart rate, pulse oxygen, blood oxygen levels, skin temperature. We also have output modules. In this case, this is an LRA for haptic feedback, but we also have a speaker in the sensor module, as well as microphones that you can interact with the device, both over voice and also have a haptic feedback. Here I have a short overview of the features. So you can see what we're going for is really a feature set that is comparable with state-of-the-art devices. So the sensor module, as I mentioned, allows us to record the heart rate, blood oxygen. We have an absolute pressure sensor. The haptic feedback engine, as I said, is a small linear resonant actuator. You can see that in the bottom section right beneath the battery. And then, of course, also, as you would find with most smartwatches, a QI charging, wireless charging. We do still have the USB-C interface as an auxiliary method of charging the watch, but this is really meant more for debugging and for easy firmware development, which is of course important if you'd like to invite collaboration, especially for firmware customizations, custom widgets, and so on. The compute module, we are using a dual-core A35 SoC. We're using the IMX8 ULP to be exact. Attached to that, we have 2 GB of LPDDR4X memory, 16 GB of eMMC storage. Those are also the 2 components that take up most of the board space at the moment. I show you later on how we are planning to further reduce that footprint. Other than that, we also have the digital crown, which is basically a rotary encoder that can also be pushed. So we have a small tactile switch behind the rotary crown. So you have 2 dimensions of input that you can give over this I/O module. Then also we have a small IMU and a compass. The display module, as I've mentioned, we have a touch AMOLED display, and also integrated in the display module is the NFC and Wi-Fi and Bluetooth antenna. There is really no other option to place the antenna. Of course, we have a solid aluminum frame, so the only other option you have is integrating a cavity antenna or slot antenna in the aluminum frame itself. On the back side, of course, if you wear the smartwatch, you'll be in close proximity with your arm, meaning there's also no option to radiate anywhere from there. So we have to radiate basically through the display, or to be exact, through a small slot on the side of the display module. But I show you how that is implemented a little bit later on. So let's start and dive a little bit deeper into the construction of the watch itself. I would like to highlight especially the PCBs that we're using. What you can see here is the first HDI PCB. It's a 6-layer, any layer design. We're using that for the sensor module. The whole PCB is only 0.4 millimeters thick, which is very important because we are trying to optimize the battery volume, meaning every component that sits underneath the battery needs to be as thin as possible so that we can make the battery as large as possible, have a longest possible battery life, and so on. And that is one way to go about that, by using a very thin stack-ups, and therefore relatively thin PCBs. And then, of course, to interface with the rest of the system, we have a standard 2-layer flex PCB. We do have some passive components on there as well. For those boards, we're going with 01 or 05 passives just because of the space constraints. But other than that, this is a relatively standard flex board. As you can see from the geometry, we have matching patterns on the FPC and on the sensor board, and those are there because we are soldering the FPC directly to the sensor board. So what we're doing here is we have designed a manufacturing jig, a solder jig, which is basically just a solder press that, after the assembly process of the sensor board, overlays the FPC on top, presses down with a stamp that is heated up to, of course, liquid temperature of our solder, and therefore bonds the FPC directly to the sensor board. We've decided to go with this approach because in mass manufacturing it's cheaper. Of course, tooling is an upfront cost, and therefore ensuring reliability and high yields is also an upfront cost, but the running costs, operational costs are much lower than going with, for example, a board-to-board interconnect. The other drawback of a board-to-board interconnect, standard board-to-board connector, would be the Z height that we are adding. So as you can imagine, at the moment, the total height by soldering the FPC directly to the sensor board is only 0.2 millimeters. We're only adding 0.2 millimeters to the existing sensor board. If we were to use, for example, a board-to-board connector, even the small pitch board-to-board connector with 0.3 millimeter pitch or 0.25 millimeter pitch, even those still add usually about 0.5 to 0.7 millimeters of additional height. And we would like to avoid that, again, because what we're trying here to is really optimize for battery volume. The second module we can take a quick look at is the compute module, the compute unit. There we have also two flex PCBs. One flex PCB is responsible for detecting the movement or the rotation of the digital crown. What we're using here is a optical tracking chip, which uses a small laser module to send out light that is reflected off the rotary shaft and then registered by a small sensor matrix in the optical tracking chip. And on the back of this FPC, we also have a small tactile button that will act as the tactile input for the digital crown. The second FPC that sits on the USB-C connector is actually there to register a button press. So we are using a plug in the USB-C connector, which acts as a push button. And what we are trying to do is sense the push button action through the casing or through the shell of the USB-C connector, because we do not want to use the USB-C contacts, the contacts that the USB-C connector provides, because, well, the button will be pressed several times a day, and we don't want to wear down the contacts on the USB-C connector. That's why we decided to go for this inductive sensing approach that can sense through the shell of the USB-C connector. And then, of course, on the main board, we have our SiP, which is at the moment a 10-layer, any-layer stackup as well. This SiP will be merged into the main board in the future. We have several reasons for that. I will go into that a little bit later on. But at the moment, it's still a separate module, the one you can see here on the right side of the screen. It's 23 by 18 millimeters large. And as you can see, most of the area is taken up by the memory and the DRAM. So the large package on the right side of the SiP, that's an eMCP. So it's an integrated package that has both eMMC and the DRAM dies integrated into one package. And our goal is in the future to stack those memory chips on top of the SoC, but again, I will show a little bit more later on about that. Then, of course, as you can imagine, the display module is mostly just FPCs folded in on itself and around itself. So we have, for example, this is the antenna FPC that houses the coils for the NFC antenna, and also provides connectivity to the ambient light sensor. That's the small PCB. How would you call it? Tongue, basically, that sits in this larger cutout. This ambient light sensor will look through a window in the metallization of the back of the display. So that way you won't be able to see it from the outside, but the sensor can still register the ambient light through the display, through the AMOLED module itself. And then we have, of course, a few FPCs to connect to the main board. So this is still one thing that we would like to try and get rid of in the future. At the moment, if you're taking apart the watch, it's still all connected via FPCs. This is, of course, something that's a little bit fragile. Those high-density interconnects are relatively fragile. They're also not that easy to plug back in. So what we would like to have in the future is ideally a spring-loaded approach using spring-loaded contacts, but this is very difficult to do given that we have to transfer high-speed interfaces like the DSI interface from the display to the mainboard. So this is something that we will look into later on. Maybe that will result, for example, in the mainboard sitting also behind the display module. But for now, we still have those FPCs to connect between the compute module, the display, and the compute module and the sensor board. So now I've already mentioned the SIP. I want to talk briefly about what we actually mean by SIP, because in the classical context, an SIP is something, it's of course system package, where you would use substrates with a very fine trace width and trace spacing, because in most of the cases you're just interfacing with the silicon die directly, meaning you have your silicon die with copper pillars, copper bumps, for example, with a very fine pitch. Those go down to, let's say, 150 or 120 microns in pitch, meaning there's really no other way around than to interface with those silicon dies, for example, with 10 or 15 microns space width and tracing. So these are then manufactured in semi-additive processes, and that's, as I've highlighted here, the region where you would find the typical system in packages. What we are doing instead, to keep the cost down and also to make the design more accessible, we are using manufacturing processes that allow for trace width and trace spacing between 15 to 100 microns. And of course, that also means that we can only use packaged ICs. By packaged, I mean, as you can see here, it's still wafer level packages, but on the bottom of those packages, you have your typical redistribution layer that basically fans out the silicon die to your 0.4 millimeter or 0.5 millimeter standard BGA footprint. So the RDL in this case is the gap between the silicon and the SIP that we are building. The SIP itself, of course, then will still be overmolded. We have a resin encapsulation. Also, we'll also be plating the encapsulated module so that you can use it in a standard SMT process. It's still packaged in probably a tray because of the size, and then it can just be placed on the board as a standard BGA, or in this case LGA component. So yeah, let's dive a little bit deeper into the PCB technology. What I would like to highlight first, of course, is the any-layer construction. In our specific case, we're using only stacked vias. We do that for several reasons, because, of course, stacked vias are much more space-saving. If we were to use staggered vias, in contrast, you would have to connect your via transition with small traces or small stubs on the inner layers. Those are then usually the ground or the power layers. And we would like to optimize the space that we have on those layers, both for signal integrity purposes, so uninterrupted return path, but also we would like to have as much copper area as possible on the power plane layers for the PDN network. Yeah, here's a good example for that. On the left side, you can see, of course, staggered via arrangement with little traces between the laser vias, and on the right-hand side, you can see a stacked via approach. And there you can already see the ground plane on the left side is cut up. There you have to be very careful where you route your traces on the signal layers, if those are referencing to those ground layers, so that you're not creating any gaps in your return path. With stacked vias, this is of course not an issue. We can drop down from the top layer to any layer we want, hence the name, and makes just signal integrity much easier, increases our routing density, and with that also our component density. There's also another benefit to using stacked vias. In contrast to staggered vias, stacked vias have to be filled with copper in order to be able to stack them on top. Otherwise, that wouldn't be possible. And that way we can basically create a solid copper pillar from the top layer to the bottom layer, which is ideal if we are trying to cool components on the top layer. This is actually a mode that is used for many SoCs that are used in wearable or mobile applications. So smartphone, for example, is a good application to illustrate that. In your smartphone, the PCB usually takes about 30 to 40% of the total heat flux just by conducting the heat away through the ground pins and the power pins of your SoC, which is also necessary because in many of those applications, the memory is stacked directly on top of the SoC in a package-on-package fashion. And by doing so, you create a little air gap between the memory chip and the SoC. And this air gap, of course, also adds thermal resistance, meaning you are limited in how much heat you can actually get out of the system through the top of the package. So having a PCB that's also optimized for thermals is really critical in those applications. So as you can see here, of course, the thermal path through filled stacked vias is much shorter and a much lower thermal resistance than compared to staggered vias. But while stacking vias also has its challenges, and one of those challenges definitely is reliability. So the IPC tells us ideally we would like to avoid to stack more than 2 microvires. We can still do so, but that requires extensive reliability testing from the PCB manufacturer to actually ensure that the vias do survive temperature cycling, for example, both during reflow, but also during everyday use of the device. Because what will happen during those temperature cycles, as you can see here, the substrate, the prepregs, they will expand or contract depending on what our starting temperature is, and they will exert a force on the vias itself. And this force then also usually concentrates on the most sensitive part of the vias, which is the section we are connecting to the next layer. And then vias usually crack at exactly those positions. And optimizing your material selection for that is really critical if you're planning to stack more than 2 or 3 vias on top. The way we've dealt with that here is by using the advanced HDI boards with a quite neat material. So that's the material data sheet, or a screenshot of the material data sheet you can see on the right side. And there you can see we have 2 values that are important for us when we're talking about reliability. One is the coefficient for thermal expansion, the CTE, which is very low in this case. It's only 4 to 6 ppm per degree Celsius. And also what we are interested in is the Young's modulus. So that basically tells us how stiff the material is. The elasticity module in this case is relatively high. As you can see, it's 30 to 32 gigapascals. Usually, just to compare that with FR4, this would be 17 to 24 gigapascals. But since we only have a thermal CTE of 4 to 6, even though we have a stiff base substrate, we won't exert much force on the vias because the material does not expand much over temperature. You could also flip that around. So let's say you have a material with a very high CTE that would still be acceptable if your material has a very low modulus in return. So, but in short, the material is very well suited for these kind of applications. And what also adds, of course, to the reliability is the fact that the material is very thin. So as you can see in the layer stack, we are only talking about 30 microns of thickness for the substrate, meaning that over this distance during thermal cycling, we won't see much deviations from the original starting thickness. Another thing that's very important, especially if building an SiP, is bow and twist. So meaning you have to make sure the PCB stays flat during soldering, but also again during everyday use. And this is especially critical in our case because we're using an asymmetric stackup. Meaning what we are doing with the SiP is placing all the decoupling capacitors directly next to the SoC. That also means we would like to have the power planes as close to the top layer as possible. And what that results in is that we have a higher copper fill factor in the upper section of the stackup. And since we have to push the signal layers to the lower half of the stackup, we have a lower fill factor in this region of the stackup. And this creates an imbalance in the copper fill factor over the whole layer stack. That would usually result in deformation of the PCB, so in warpage or twists during reflow or during, again, everyday use. So in order to model if this is really an issue for us, we have run a simulation where we basically simplified the trace geometry. We've transformed that into a density pattern, the one that you can see here on the right. And we've done that so that we can more efficiently simulate the bow and twist of the whole stackup. So those little squares, they are increased in discrete steps depending on the copper density that you can see on the left side. And those discrete steps also are the same size as our simulation mesh. So what we would like to do is use a hexahedral mesh for most efficient simulation, also highest accuracy. And therefore we decided to create this density map with just squares that are representing the copper density, and the dimensions of the squares are adjusted in discrete steps that we are also using in the mesh size. So that allows us to run very fast simulations on the bow and twist of the PCB. And yeah, the results look very promising and also have proven to be correct in our first production runs. We see about a 28 micron displacement from the middle of the module to the corners of the module. This is of course only important during the first reflow cycle. Once we have the components on the board and the solder is cooled and solid, then the whole mechanical properties of the stackup will change, of course. But at least for the first assembly step, and to guarantee the planarity of the finished SiP, we are safe in this case. I can also show you this here with the laser pointer. There you can see the two signal layers in the bottom half of the layer stack. Those are much thinner than the remaining layers. So what we've done here is just normalize the thickness of those layers depending, in dependency of the fill factor. And there you can also see why the whole bottom half of the layer stack has a lower copper density. What we are planning now for the next step of miniaturization are two things. One thing is we would like to embed the inductors of our power management IC into the SiP itself. These inductors are also something that Würth Elektronik is developing currently. So we had the chance to have a custom design on the multi-project wafer that was customized to our needs or to the specific PMIC that we are using. And that way we can create more space on the top layers. Of course, you also have to be careful that this is an unshielded inductor, so you will have stray fields above and below the inductors. But since we still have a permeable core in the inductor, embedded in the inductor, the field distribution does not look like your typical coreless planar inductor. So compared to that, the eddy currents that you have to expect above or below the inductors are still reduced, but still wouldn't be recommended to route any sensitive signals directly above the inductors. And the second step, I already mentioned that before. At the moment, the DRAM and the EMC take up most of the board space, which is just due to the fact that they are packaged in a multi-chip package and arranged besides the SoC or next to the SoC. And what we like to do next is basically stack or glue bare dies directly on top of the SoC and wire bond those dies down to the substrate. That way we have a little bit more C height, but we gain a lot of space in the XY plane, and that's where we need it at the moment. That also gives us more option where to place the battery. We could also place the battery next to the main board because it gets so small. So these are things that we would like to explore in the next design iteration. But for now, we will continue with the SiP designer, as I will also show you in just a second here on Altium Designer. For qualifying the embedded inductors, what we're doing, we have designed a small power module that uses the same power management IC that we're also using on the SiP. That power module allows us to manufacture this embedded inductor approach relatively cheap, and we can also characterize its thermal performance. For example, we can characterize the output ports, of course, and that way just iterate quickly on the inductor design without having to manufacture the whole SiP from start to finish. I can also show you how that looks like. So in the middle of the layer stack, we have a relatively thick core that's 290 microns in height. And there we can basically place the inductor in a small cavity within that core, and then directly connect the inductors in the next plating cycle. So the inductors itself will be connected with microvias as well, which is very convenient design-wise, but also is a very streamlined manufacturing process. So this is what we are planning then for the next step of the SiP. But yeah, let's take a look at the design. I think I will start with just giving you a brief view over the mechanical design. This is just a step export, so some dependencies are missing, but I think it's still fine, just to give you a rough understanding of how the mechanical design looks like. So as I've mentioned, on the bottom side, we have our sensor module. The sensor module, as mentioned, is the small any-layer stackup that houses the photodiodes, but also the LEDs for the PPG sensing unit. And on the PPG sensing unit, we also, of course, have local regulation, because low noise design is very important for this PPG module. We're dealing here with a 24-bit ADC with up to 120 dB dynamic range and very low signal levels. So it's really important in this PCB to keep good separation between our digital section and analog section. And this is especially easy with the NLR stackup. I will show you that in just a second. But other than that, let me hide everything else. You can take a better look. Yes, there we go. So here you can see now only the sensor module. You can see the large battery sits directly over the sensing unit itself. The sensing unit can be seen here. This is the small PCB I've just shown you a minute ago. And we have the FPC that connects to the rest of the system. This FPC, as mentioned, is soldered directly to the sensor board. You will notice a larger ring around the sensor module. This is the QI charging coil. We don't really have any difficulties with voltages induced in the sensing module or in the FPC. That's for two reasons. One reason is we're using a ferrite sheet or ferrite core behind the QI charging coil, both for shielding purposes, but also to increase the coupling factor with the transmitter. And the other reason is that once you actually generate a current in the receiver coil, your fields will be displaced to just or will be concentrated in the gap between the transmitter and receiver coil. So in the middle of the coil, we do not see a high field strength, and therefore also not see high voltages induced or currents induced in the sensor PCB. Yeah, on top of the sensor PCB, we then have the watch body that holds only the PCB. As you can see underneath the shielding can, there we currently have the SiP. As I've mentioned, this will be merged into the main board itself, just to create a little bit more space, because we are saving then, of course, 0.6 millimeters in the PCB thickness. So that can be used, of course, later on for additional battery volume. In the middle section, I can show you the construction of the rotary encoder real quick. We have a PCB that basically folds around this little plastic part, and that creates the option to have the optical tracking chip that's viewing mostly the side of the rotary encoder shaft, and behind that we have our small tactile switch just to give the tactile feedback. On top of that, then we only have the display assembly left. There's not really much exciting going on. As I've mentioned before, it's mostly flex boards. Of course, the flex board for the OLED display itself, but then also the flex board for the antenna. And here you can also see where the antenna for Wi-Fi and Bluetooth is integrated. It runs along the side of the display frame. And in future, this will be changed over to an MID design, meaning metallization directly on the plastic part. So let's take a quick look in Altium Designer. So this, for example, is the SiP itself. We can open up the layer stack here real quick. So this is a neat thing. For example, if you decide to use the ADVANCED.hdi technology, you can just download the layer stack. It then includes your impedance profiles and your via types, so you don't really have to worry about setting that up manually. And of course, coming directly from the manufacturer, it's a reliable source of truth in this case, if you will. But yeah, the SiP design, as I've mentioned, is a little bit special in that we are using the decoupling capacitors right next to the SoC. Those are also feed-through type capacitors, as you can see from the footprint. This is just done in order to reduce the series inductance, the parasitic inductance of those caps, because we do have, of course, an increased distance to the power pins by placing them directly or next to the SoC, meaning we would like to minimize the parasitic inductance in all the other elements that we are adding here in series of those capacitors. So in that case, we would like to keep the vias as short as possible. That means we would like to just change from the top layer to the first or the second inner layer to keep those distances as short as possible. And then, of course, due to the very thin materials, we have a relatively high interplane capacitance, which takes then care of the impedance response in the very high frequencies. Additionally, the requirements for this SoC are relatively loose when it comes to the PDN, so we are not seeing any issues with the distribution network. This would be a different story for different SoCs, but of course, depending on the speed grade and depending on the interfaces, every SoC has different requirements on the PDN. So this approach wouldn't work for every SoC. But yeah, just skipping through that here real quick. As you can see, those are the power layers on the first, on the second and third inner layer, and then on inner layer 6 and 8, we have the signal routing for all the interfaces, both to the DRAM, but also for the interfaces that go to the outside. So this is one of the HDI stackups that we're using. The other one is for the sensor board. As I've mentioned, what was very important here is keeping the analog and the digital section separated. You can even see that we had to use a cutout underneath the LEDs, which are driven by the digital section or supplied by the digital section, meaning we have to expect some noise on those signals here. And we do not want to couple this noise capacitively into the analog ground plane, which is why we have cut out in the analog ground plane, which is the deep blue section you can see here. And this is then only reference to the digital ground section on one layer below. So that's how the construction looks like for this sensor board. And the one I wanted to show you as well to give a better impression of how the construction of this digital ground looks like. It's basically only a standard flex board with the optical tracking chip on the bottom side and the tactile switch on the top side. And what we're doing then is basically folding this flex board around the plastic carrier that will then be assembled onto the main board and thus have the functionality for both acquiring the positional data of the rotary, or not rotary encoder, of the digital crown, but also being able to have tactile input all in one unit.
So many thanks to Lukas for the interesting presentation and background details. As you all certainly know, the new components are becoming smaller, more powerful, and more functions. This means for you that the layout design is more complex as before. Isn't it, from a component footprint, size, BGA pitch from of 0.35 millimeter and smaller, is very important that you need other design rules as before. Here our special advanced design rules and the very important parameters are in line and space. So you can use overall layers, top and bottom too, with 75 microns, or 50 microns are possible too. And the next very important parameter is the finished head size diameter from less than 220 microns up to 200 microns. This is very important about this one. So you can use for small footprints. And the next big step is the solder mask. The solder mask is a very critical process, and so here we can from the switches, and you can go less to 35 microns clearance, and so you have an option to make for these parameters to use by BGA components with 0.3 millimeter pitches. On the next slide, I have a special storytelling. It is a customer inquiry with the following details. They come with us with a HDI PCB, standard build-up, 1.6 millimeters thickness, built up with buried wires, 4-layer, and all you can read in the report is standard, no problem. But after reviewing the data set, we make a design rule check. Here we found buried wires with pad size 0.3 millimeter and the finish hole diameter with 0.15 millimeter. For us, it is a process with O tolerances. So we have the end-ring from 0.0 microns. And the next, we have through-hole wires from top to bottom side with the same parameters, 0.3 millimeter pad size with finished hole diameter 0.15 millimeter, and so this is not possible to do this. And the next one, we found line and spacing on the outside top and bottom layer with 30 microns line and spacing. And the next problem was a solder mask with 50 micron bridges and with clearance 0.0 microns. Not possible. So what we do, we tell with our customers, say, sorry, this is not possible. We can have a lot of other parameters with our slim HDI technology, and here we can use a thinner board, thinner materials, smaller pad size, and then our customer make a redesign, and so he get a PCB for his components, and so it is possible to do this. The background, they use a 1 BGA component with a 0.35 standard HDI parameters. Our physical PCB samples will be available shortly, and this will show some details from today's webinar. In addition, we use a special temperature cycling resistant base material with very low thermal expansive CTE and significantly reduced bow and twist. Adapting to the expansion of silicon offers advanced when using air dies and or wire bonding technologies. And we make a lot of test vehicles in our release process. So we make 10 times reflow testing with a peak temperature from 260 degrees. After this, we make a resistor testing from the microvia connections, and we saw all is fine. After them, we make a 500 temp shock cycle test with minus 55 degrees up to 150 degrees. After this 500 cycles, we make the resistor testing too, and we saw all was fine. No connections, all connections, no cracks, no different resistor results are here. So you can see the thin material and the special parameters from the material make a very, very stable PCB about this one. So we have additional further physical PCB samples are available to you that make the different technologies for you. For example, on the left side, you see for the same technology as actually as Slim HDI, the Slim Flex sample, then a polymer sample, HDI standard samples, and a lot of 3D rigid flex samples. Here you find with flex on the outer layer, flex on the inner layer, and so on. You can place and order this on our homepage. You can find on top side directly of our homepage, and then you can order it every day. So then, thank you very much for your attention. We hope our webinar was provide for you with a lot of helpful information, and I hope we can hear you and see you later. Bye-bye.